What up, guys? Welcome. Welcome back. I'm trying to stay very consistent in this journey. I do not want to backslide. So, welcome once again. Today, we're going to tackle the quantum mechanical model, maybe the final part if we have time, because I do not want the video to be so long. Maybe I'll do it all in one shot and cut it into two. So, you can watch it in separate times. But today we will try our best to cover most of the quantum mechanical model of the atom before we move on to periodic chemistry, which is chapter 2 of the MCAT chemistry, where they test that pretty much. So to set the ball rolling, after Rutherford, which was around 1913, predicted the classical model of the atom, whereby he said that the atom is going to be something like with a positive dense nucleus, which is proton, like a positive dense nucleus like this. My marker is misbehaving. Like a positive dense nucleus, and then you have the electrons in it stuck into it. Right. So this was the model that they used, and this model was the Rutherford's model, right? Was what they were using most. But then a question arose that, well, it might not be this, it might not be like this. Why? Because classical physicists postulated that energy is continuous, because if you playing a guitar or a string, the sound comes continuous. They assume that energy, as in light energy, could also be continuous. But a scientist from that time after Rutherford called Maxwell Planck, he started this journey 13 years, I think it was 11 years after Rutherford had done his model. He came in and then said energy is not continuous. Energy is released in discrete packets. So he said energy, it comes in discrete packets. Forget my spellings, guys. It comes in discrete packets. So why would he say that energy comes in discrete packets? Is a whole lot of charade if you want to go down into there, but then the MCAT doesn't really go deep down. But at the ballpark of what they were trying to figure out was that a black body, which is a theoretical body that would absorb all energy incidented on it and release a radiation based on its temperature. If energy comes in a continuous form, then a black body should continue releasing infinite amount of energy in the ultraviolet region. But no, that was not the case. They realized that black bodies do not release infinite energy. It is also physically impossible because any energy can either be created or destroyed. So if I'm releasing infinite amount of energy, it means I'm feeding something infinite energy also. So when Maxwell Planck came and then he kind of, bombarded get rid of the idea that energy flows in continuous. He also said that energy, when it comes in a discrete pack, could be related with this equation: energy equals to H frequency, right? Where H is the Maxwell-Planck's constant or Planck's constant. And this constant is a constant of proportionality, right? It comes from black body experiment, right? So if you take the black body curve, you have a classical physicist taught that the intensity or the radiation on the y-axis is directly proportional to the frequency that you graph of a black body. This is how classical physicists taught. A guy who made this popular was called I think it's Lenz's law. If you've done it more into theoretical physics, you know this law, but the MCAT doesn't really focus much on there. When Maxwell Planck came, he said that energy is released in discrete packets as it goes like this. It hits a peak and then it descends down. It does not continue all the way to infinity. Stops somewhere, then descend down. So as you can see, the first part of the curve is kind of true. It's kind of common with both the classical and then the quantum physics understanding of energy. But as you go up, they differ. So this one became it was not used anymore, and then this became the standard. As you plot the intensity versus frequency graph in a black body experiment, which we are not going to do that, you'll find the constant, the proportionality constant, which is Planck's constant, to be equals to 6.626 times 10 raised to the power negative 34 joules second, right? So this is the Planck's constant, and you should try to keep this in mind, memorize it, keep in mind 6.626 times 10 raised to the power negative 34 joules per second. So after Maxwell, Planck has done this and has come up with the Planck's constant. Over here, another scientist arose, right, goes by the name Niels Bohr. He started looking at hydrogen atom, and then over there he equated hydrogen atom to our solar system, whereby you have the sun, which is the nucleus of the hydrogen atom, and then the planet, which are the electrons revolving around the planet, right? So let's go to the Bohr's model, right, of hydrogen atom, of H atom, right? So he said that the core, which is the nucleus, right, and which is the sun, revolving around by an electron, right? Let's just, represent the electron with another color over there. This is how Niels Bohr described the hydrogen atom. But then according to classical physics, if you have an object moving around a circular path like this, then the object can assume an infinite number of kinetic energy and angular momentum, right? Because it can go, if you are like depending on an infinite amount of radius. So the radius could change infinitely. So if radius change infinitely, which means this angular momentum will change infinitely, because the angular momentum depends on the radius. And if the angular momentum can change infinitely, then the kinetic energy can also change to infinity, which the kinetic energy also depends on the angular momentum. So if that is the case, then we cannot properly calculate most variables that we do want to calculate for. So Bohr decided to incorporate Maxwell's Planck theory that energy comes in discrete packet, and then imposed it on his hydrogen atom model. Now, when we say energy comes in discrete packets, they call those discrete packets as quanta. Quanta is a Greek word that means how much, like how much of a substance, how much, right? So if it comes in a discrete quanta, it means the amount or the bandwidth with which the energy can exist in is fixed. It does not flow continuously like water. If it flows continuously like water, then it can keep on going for infinity. But energy doesn't work like that. It comes in short quantas. So it coming in short quantas, you can imagine energy as the Star Wars or Star Trek lasers, like when the Star Troopers shoot the laser gun, how the energy, the fire comes out like in those short bursts. It doesn't go all the ways to hit the target. It comes in short bursts. That's the exact way how energy works. So Niels Bohr decided to take Planck's ideology and then fix it to his hydrogen atom. So he said that if energy comes in short quantas, then electrons can only exist in those quantas. And that for a real life representation of it, we can take the electrons as existing in the hydrogen atom as a staircase, right? As a staircase versus a ramp. So if you have a staircase like this, you have a staircase. Let's go through. Or you have an inclined plane, which in other words is a ramp, right? If an electron exists around the hydrogen atom, right, and then it is going in an orbit around the hydrogen atom, it can only exist in a certain quanta of energy or on a certain energy level. So in this case, it can either exist on energy level 1, energy level 2, energy level 3, all the way to whatever energy level that the particular atom has. So when we talk about this, if an electron is over here and then it wants to move to energy level 2, right? It has to have a specific bandwidth. Like if you are walking up a stairs and you are on the first step of the stairs and you want to go to the second step of the stairs, you have to lift your leg just so much that you have the right amount of height or the right amount of distance to cover the stairs so that you can step your feet onto the next level of the stairs. It's exactly like this. The electron has to absorb enough energy, just so enough that it is enough to overcome this barrier here and then go on to the next level. And if you do that, that means the amount of energy, like the energy that you're going to need, is fixed. Is this level of energy, right? The energy between here and here is fixed. If you get energy between, let's say you cut this into half here and then here, it's not, your electron is never going to go here. You have to have the exact amount before the electron can go. So this is what Planck said. But at that time, the classical physics was also saying that if energy comes in a continuous form, then the electron sitting around the hydrogen atom should have the infinite amount of energy. That means if you put it in this case, like if you're moving up a ramp, you are at the bottom part of the ramp and you want to go to the top part of the ramp, right? Let's say you are an electron, right? Theoretically speaking, you can take infinite amount of stairs to get here or amount of steps to get here. Like you could take your time and take like tiny steps, tiny steps. Like to how much of height you should lift your feet and to how far you should place your feet. It's not bounded to anything. You could take it as tiny as possible or as big as possible. And whatever you do, you are going to move forward, provided you don't step back. So that is how the energy works. Now let's get rid of this. If you have any question, drop it in the comment section. So let's come back to Bohr here. After Bohr said that, and then he said energy, the electron has to exist in a quantized or an energy level around the electron in a specific orbit around the nucleus of an atom. That was what he meant. So therefore, the angular momentum, the classical formula for an angular momentum, L is equals to mass times the velocity times the radius, right? He said this classical formula, which can assume any value depending on the radius, how wide the radius is from the atom or how fast it is going, can assume any value. It's not like that. We got to bound it to a specific amount of values it can have, like put it in a bandwidth. So putting it in a bandwidth, Neil Bohr said that this momentum, angular momentum, wouldn't work if we are saying that the atom has to, or the electron has to exist in a specific bandwidth. In that case, we have to put the electron in a specific, just a range or in a specific energy level. So he said the angular momentum is equals to the n, which is quantum number, in this case, the energy level, quantum number is the energy level, times the Planck's constant, which is the constant of proportionality, divided by 2 pi. Right now, if you see 2 pi, if you've done circle theory, you know 2 pi radius is the circumference of the circle, which in this case would be the orbital radius, right? So this was the energy, the angular momentum of an electron. So this angular momentum of an electron. So once again, the angular momentum of an electron orbiting around a hydrogen atom, Niels Bohr said it is n, which is the principal quantum number. Principal quantum number, which is also equals to the energy level. And then h, which is Planck's constant, which is equals to 6.626 times 10 power negative 34 joules second. Now, we've gotten this. After he's saying that the angular momentum can only take certain figures because of the quantum number, because if this changes from 1 to 2, it changes the whole solution to 3, 4. However value this thing takes on determines what value the angular momentum is going to be. He said that since that is the case, then the energy that an electron can occupy around the hydrogen atom also has to take on a specific quantum energy levels. So he equated that, or he said the energy of the electron is equals to negative RH divided by n squared. This R here is called Rydberg unit of energy, right? The Rydberg unit of energy, which is equals to 2.18 times 10 raised to the power negative 18 joules. Negative 18 joules per every electron. Now we can go on and on to discuss how we came out with this RH number, but then we're not going to go deep into that because this is like a rabbit hole. If you dig into it, you are not going to come out. So we take the face value understanding of it. Now, the most important thing here is that these equations are complex. They are complex equations. Like, look at this figure, right? Like some exponent 18, look at this, exponent 34. And on the MCAT, what it will test for is not your ability to check in, which is important. Your ability to do calculations without a calculator is important, but that is not what the MCAT is going to test. The MCAT is going to test proportionality. It's going to test what happens to this value if, say, this changes. What happens to this if this changes? It's going to test you the ratios and then the proportions of these equations. So if you know which unit relates to which unit, and you could do that by just memorizing the equation, you will know which unit relates to which unit. So if the MCAT asks you what happens to the energy of an electron if the principal quantum number changes, you then have a point to make an assertion. But this equation comes on in a very tricky way, because if you look at this equation at the first glance, you think that the energy that the electron, let's say I pick n equals to 1 at the one quantum level, or at the one energy level, or at the one principal quantum level, my calculation will be 2.18 times 10 raised to the power negative 18 joules second, right, divided by 1 square. So the negative is here. 1 square is 1. So my answer is going to be negative 2.18 times 10 raised to the power negative 18 joules second. Right. It's still negative. It's negative. The answer here is negative. But then let's say the next time I calculate n equals to 2, which gives me E equals to 2.18 times 10 raised to the power negative 18 joules second divided by 2 square. Right? All of a sudden, I get my answer to be 2.18 times 10 minus 18 joule second divided 4, because 2 square is 4. Now it's going to be, let's say we take here 2, 2 goes here 1. It goes here 2. So 1 over 2, which is half, which is 0.5, right? So the answer is going to be, say, 0.5. This is a rough figure, but it's 0.518 times 10 raised to the power negative 18 joules second. But the answer is still negative because there is a negative value when we started calculating. The original formula has a negative value in it. So our answer here is still negative. The catch is that this is negative, but it is a bigger negative, right? Oh, this is negative, but then it is a bigger negative. Negative 2 and negative half, which number is bigger? Right? Negative half is bigger than negative 2 because it's approaching 0. Negative half will get to 0 faster than negative 2 can get to 0. So that makes this equation a direct proportionality. Thank you. If you have any question, you can leave it in the comment section. And then also, if you say, what about the Rydberg unit of energy? It's a constant. It doesn't change. So there is no way it's going to be bigger or smaller for you to make a proportionality relation between it and the energy. It's always constant. So in fact, after Niels Bohr and Planck say energy is quantized, and Albert Einstein also say light energy is also quantized. Bohr used this information to do his hydrogen atom. Like they all won Nobel Prizes for the work that they did for physics. Now that brought us into emission and absorption spectra. Right. And to tackle this, we could go into the line spectra, but we are not going to really go into the innuendos of it, just to cut us into what is really important. Now, to start emission and absorption spectra, atoms would always take stability over energy consumption. They always want to be stable. So any atom that you are likely to find in nature is in ground state. The ground state means it is stable. There is no energy incidented on it. It is where it want to be. Stable. It's comfortable. Right. But then, what if we excite atoms? Right? In other words, we give them energy or we bombard them energy so that they change, their electrons will change the quantum state or the quantum energy level that they are occupying. That is what brought us into emission and absorption spectrum. Now, if you have an atom with a nucleus, and then for Niels Bohr, the number 1 quantum level, number 2 quantum level, and number 3 quantum level. If you have an atom like this, they are always stable. You would find their electrons in its ground state, meaning it is occupying the distance closest to the nucleus where they can occupy without expensing energy, right? But then if an electron is occupying a state, let's say it is occupying the n-2 state over here, but it wants to become stable, it wants to go to the ground state, to become stable. In this stage, it is what? Excited. You want to go to become this state, the n-1 state over here, right? What does it do? Remember that when we were saying that energy is quantized, we use staircase, for example, right? That if you have a staircase like this, an electron can exist in quantum number 1, quantum number 2, quantum number 3. So in this case, the electron was existing in quantum number 2. That is its excited state, right? But it wants to move to quantum number 1, the ground state, where it is most stable over here. What does it have to do to get here? Leave it in the comment section. So it has to lose or release the amount of energy directly equal to the energy difference between the states, right? Between the level 1 and then the level 2 states. That is the amount of energy this electron has to release. And since that energy is released, once we said energy comes in quanta, it will be released in a packet. That packet, this bandwidth of energy, that packet of energy right here, right? This bandwidth of energy right here, the energy difference between states, is called a photon. So a photon is not just like an energy, it's a bandwidth of energy. So it will release it in the form of a photon, it will boil up the energy and throw it away. So that photon has energies. You get what I mean? And it will throw it away. Now this photon, the energy of this photon released, as the scientist said, was equal to the energy difference between the ground state, the energy difference between the higher state where it got from and then the ground state where it went to. And it's emitting this photon, releasing this photon out is called emission spectra. It released a photon. This is called emission spectra. Now, in other cases, so here we are going to release a photon. We're going to release a photon. Let's make the green dot a photon. We will release a photon. That is it. Now, in the same situation, right? In the same situation, but in the reverse, if an atom is here, as like the first one that we said, if it's here and it wants to go, like we want to excite the atom, we want to force it to move an electron from, let's say, the n-1, the n1 state, 2 state, 3 state, from the n1 state to the n2 state over here. We want to move the electron over here. What do we still have to do? We have to give the electron enough energy that should be exactly between the energy difference, or should be exactly the energy difference between the stage that we want it is currently at and the state that we want it to be. So in this case, stage 1 and then stage 2. So this energy here is what we need to give it. A bandwidth of energy is what we need to give it. And then this bandwidth of energy is what we call, again, a photon. Right? So if you want to go up, we shoot it with a photon. Photon, if it wants to come down, it gives us the photon. So we shooting it a photon and giving us a photon. Now look at it. It was 1, we jumped it to 2. It was 2, we jumped it to 1, it gave us a photon. It was 1, we gave it a photon to shoot it into 2. So the amount of photon that is needed to jump it from 1 to 2 is the same as the amount of photon that it is needed to also release it from 2 to 1. You get what I'm saying? This is the law of conservation of energy. The photon you give should be the photon you release. So they came out with this relation that the photon you relieve or give to the electron to make it jump, the energy of that photon is equals to HF. We already know this equation already, right? Or it could be HC over lambda, right? Now, where does the HC over lambda comes from, right? It comes from the frequency equation, right? Where we have C, which is the speed of light, equals to F lambda, right? The lambda is the wavelength. And if you want to make F the subject here, we get F is equals to C over lambda, because we will divide here by lambda. We divide here by lambda. Lambda cancels lambda. Then we get F equals to C over lambda. So we take all this F equals to C over lambda, and then we substitute it into where this F is. And then we get C over lambda H. So that is the equation of the energy that a photon has. It doesn't matter whether it's being jumped up or it doesn't matter whether it's being jumped down. This is it. But sometimes you would get this type of equation in the MCAT, but you wouldn't be given the Planck's constant, or maybe you wouldn't be given the speed of light, which is constant, by the way. The speed of light is 3.0 times 10 raised to the power 8 meters per second. Right. You could be given that. So or maybe the frequency. So if you are not given that, how do you go about it? Right. So sometimes, as I said, you might not be given all that. You could go about this equation. Remember this equation: the energy of an electron inhibiting a particular energy level or on the or around the orbit, the energy was given by negative RH, which the RH is what? Rydberg unit of energy divided by n square. We could go about it. So let's say our electrons are occupying n equals to 1 state and n equals to 2 state, right? So for us to find the energy difference between these two, which is the photon, the energy that the photon has, which is the energy difference between these two states, we can go on by saying it is what? The final minus the initial, right? The final minus the initial, the final state that the electron has to end up in, minus the initial state. So if we are doing it for, let's say, emission, right? It has to be the final state that the electron ended up in was a lower state, which in this case, n equals to 1 state. If it was for absorption, the final state the electron will end up in is a higher state, which is, let's say, n is equals to 2 state. But let's do it for both of them together. So we have a combined equation for both. So you don't have to memorize two equations. So let's say we're finding, generally speaking, for n equals to 1. So E1 over here, we have negative RH over N1 squared. For n is equals to 2, we have negative RH over N2 squared, right? So if you want to have the difference, now let's do it final minus initial. In this case, let's just do it 2 minus the 1, because the 2 is the bigger. So we're going to have E equals to final, which is RH1. Or if you're doing it for an emission, it would have been this, but let's go with the final, which is the 2. It's going to be negative RH all divided by N2 squared minus, into bracket, minus, right, or yes, into bracket, RH all divided by N1 squared. Now this will go into this and it will be what? Positive. So we can come here and then say that we can come here and say negative E equals to minus RH all divided by N22 plus RH all divided by N12, right? This is still a negative, right? So let's factor out RH because RH is common to both of them and it's constant too. So we're going to have RH is out of the bracket into bracket 1 over N2, 2, still minus plus 1 over N1, 1, right? But let's arrange the equation just so that we don't confuse the minus sign. So we come here and it will be E is equals to RH into bracket 1 minus N1 squared minus 1 over N2 square. See how you manipulated the equations that you already know to figure out the energy of a photon if you're only given the Rydberg unit of energy. That is how you go about it. So the ability to memorize formulas, right? So let me clean it here. And then let's say the formulas, the most important formulas that the MCAT is going to test under this topic. So formulas to remember. So what are we taking away from emission and absorption spectra? One, the energy released during an emission spectra and the energy absorbed during the emission spectra of the same atom is equal. So one, energy released during absorption and the energy released during emission of the same atom is the same. That is the energy conservation. And then two, we had these formulas, right? There are 5 formulas we need to keep up with when it comes to emission and absorption spectra. There's one, Planck's relativity equation, which is E equals to HF. And then two, the energy of a photon release, which is Hc over lambda. And then we know this equation, this is 1, 2. This equation comes from rewriting C is equals to F lambda, right? And then we put this equation into this one to get equation 2, right? So the equation 3 or equation 4 in this case is the one with the Rydberg unit of energy, which is E equals to the Rydberg unit of energy, and it's always a negative, divided by N squared. And then the equation 5 would be the manipulation of the Rydberg unit of energy, the equation with the Rydberg unit of energy. So this is the equation of the energy of the electron. If you want to find the differences between that, we can manipulate the energy of the electron to find out RH 1 over N1 squared minus 1 over N2 squared. That is what we get from emission and absorption spectra. Okay, so the emission and absorption spectra brought an idea onto or throw a lamplight into this series of emissions. Now, before Niels Bohr came up with a hydrogen model of an atom, some scientists like Theodor Lyman and Balmer, Pashkin. There are a few couple of others like Fundus and then Brackett. They have been working on an emission spectra, right, of an atom. So as when we said that the energy comes in a form of like a packet, a bandwidth, a quanta, right? This is what we meant. Like we literally meant that a photon can exist, like an energy that a photon can produce can exist in this quanta, can exist in this quanta, can exist in this quanta, and there are like two other more quantas, which is the fundus and then the brackets quanta, right? That is what we meant. So for the Lineman series, right, Theodore Lineman was working on the energy spectra of atoms that jump from wherever they are to the base quantum level, which is n is equals to 1, right? So any emission or any absorption spectra that jumps an electron from a bigger quantum state, which is n is greater than 2. So if n, which is the principal quantum number in this case here, if it's n is bigger than or equals to 2, if electron jumps from any number which is bigger than or equals to 2 to the ground state, which is 1, the emission, the radiation that it emits falls in what we call the Lyman series or the Lyman series packet of energy. So if it jumps from, say, the n is equals to 2 to the base, which is n is equals to 1, so n greater than or equals to 2 to n equals to 1 quantum number, it releases a certain type of wavelength, and that wavelength exists from anywhere from 122 nanometers to 94 nanometers. So if you jump from n equals to 2 to n equals to 1 is 122 nanometers. If n equals to 3 over here to n equals to 1 over here, it is 103 nanometers. If it jumps from up here, which is 1, 2, 3, 4, n is equals to 4 to n equals to 1, it is 97 nanometers. If it jumps from n from 5, I couldn't draw all the way up the n from 5 to n is equals to 1, the wavelength is released is 95, and from n6 to n equals to this one here is also 94 nanometers. So those are the bandwidth of energy, and as you can see, the wavelength decreases as you jump from a higher state to a lower state, right? Which means a wavelength is going to decrease, which will mean that the energy that is going to be released is going to increase, right? So that is how the Lyman series work. Same thing with a Balmer series. So the Lyman, we go to Balmer. Balmer is, and if is for him, if he was also working on electrons jumping from anywhere of n equal to or bigger than the third principal quantum number, or n is equals to or bigger than the third quantum state, to the second quantum number, to n equals to 2. So if an electron jumps from anywhere bigger than n equals to 3 to n equals to 2, not n equals to 1 as in Lineman, but to n equals to 2 over here, the bandwidth or the photon of energies that it releases is within this range, 656 nanometers if it jumps from n equals to 3 to n equals to 2, 486 nanometers if it jumps from n equals to 4 to n equals to 2, to like that. From n equals to 3, it goes on and on. Like that. Same thing works with Pashkin. It goes for the Pashkin series too. If it jumps from anywhere n bigger than or equals to 4 to n equals to 3, jumping from anywhere bigger than 3 to 3. So Lineman is jumping from anywhere bigger than 2 or anywhere bigger than 1 to 2 to that one onto itself. The Balmer series is when it jumps from anywhere equals to or bigger than 3 to 2, and then the Pascal anywhere bigger than 4 equals to 4 to 3. So that is how the units, the wavelengths comes as electrons jump from one energy state to the other energy state. Now, the MCAT is not going to require you to memorize the different wavelengths as electrons jump from one point to another. What you need to do is to put into mind the equations that we did work about, because the equations can tell you to find the energy of the photon, and if you find the energy of the photon, you can use any of those equations to also deduce the wavelength. It could also ask you for the frequency. See, so if you do, by so doing, you don't need to memorize any of these. But if you have a bigger brain and you can memorize these numbers, go ahead, do it. But if not, just know how the formulas work and they apply to these numbers. So this is just an understanding of the Lineman, Balmer, Pashkin. There are two more others like fundus or funds. I don't know how to pronounce that word. I think it's spelled like this. PFUNDS, funds, and then the bracket series, right? Forgive my spellings if it's wrong. So these jumping of electrons from one form to the other brought us to quantum numbers. Now,